inflections in shape. So here are objectives for today's lesson, right? The main idea being, by the end of this lesson, you should understand what concavity means and what inflection point is, and then how to find them, given either the function or the prime or given the second derivative. So let's kind of get into it. What is concavity? Concavity is the shape of the graph. Specifically, when it's opening up, we call that concave up. So concave up is when your graph is opening up. On interval. So you can kind of see here, right? So it's opening up on interval. Concave down is when it's opening down. Sorry, when it's facing down. On interval. A lot of people see this as like holding water. Like this one could hold water, this one can't. Like if it's a bucket or something, right? So that could hold water if you can draw it. And a little water. This one, that can't happen, right? It's gonna fall out. So that's the main idea of concavity. It's about the shape of it. If it's opening up, opening down, concave down, right? Hopefully kind of simple idea. Now what's an inflection point? It's where those two pieces meet, right? So it's opening up, then there's this point right here, then it's opening down. So it's where the concavities meet. It's called an inflection point. So how do we do this using mathematics? Well, let's actually backtrack a little bit. In our last lesson, we talked about increasing and decreasing functions. And that all came from the first derivative, right? We set the first derivative equal to 0 or undefined. And that gave us our critical points. Right, then we did a sign chart at the critical point. And if your first derivative was greater than 0, it's increasing. If your first derivative is less than 0, it's decreasing. Right, so that's how you could tell increasing decreasing by doing the first derivative. Concavity is going to be done the same way. Only difference is we're going to do it using the second derivative. Concavity. So this means first we find, well, choose we have critical points, but now since it's our second derivative, we're going to call them possible inflection points. Well, we're going to take the second derivative, set equal to 0, or undefined, just like we did before, but now we're going to call these possible inflection points because that's what they are. They're possible inflection points. We'll talk more about what makes it an inflection point, what not makes it not an inflection point. And then we'll do a sign chart with that, right? Just like we did last time, we'll do like a little sign chart for our value. Now, this time, when we do our test points, we're going to plug into the second derivative because it's a second derivative test. It's the second derivative we're talking about here. And just kind of like before, if you get a positive, this time it's going to mean concave up, positive up. And then if you get a negative, second derivative, it's concave down. Right? So it's very similar to what we did last time. If you take the second derivative and get a second derivative greater than 0, is concave up. Second derivative less than 0 is concave down. How do you find this inflection point where it switches concavity from concave down to concave up? You set the second derivative equal to 0, and that might be it, or undefined. That's a possible way of getting it. Again, we'll talk about what makes it an actual one in a bit. But that's kind of the general idea. Just like we did increasing, decreasing, same idea from concavity. Set the second derivative equal to 0 to find the possible inflection points, and then do a sign chart: positive concave up, negative concave down. So let's look at it more from a graph standpoint. Right. So looking at this graph here, let's look at this. Let's try to figure out where the concavities or inflection points are. Right here, see how it's opening down? That's concave down. So just like when we did increasing and decreasing, we'll say from that point to that point, from 0 to A, concave down. And then it kind of switches and it starts curving up, curving down right here. So another concave down from here to here. And then curving up. So those are my concave downs. Where it opens up is concave up. So see right here, it's opening up, concave up. Then it stops, it opens up again. So I have concave up from A to B, and concave up from B to C. Then right here, from D to infinity, also concave up. Now let's look at these points. So an inflection point is when your second derivative equals 0 or undefined. Second derivative, I gotta get used to that. Or undefined. And there's a sign change and the values in your domain. We'll talk about that in a bit. And your point of concavity is in the domain. So let's talk about that. So there needs to be a sign change. So look at here. You go from concave down, which would be like a negative, to concave up, which would be a positive. That's an inflection point. You switch signs. So inflection point. At A, and then wherever you plug it in at, A, FA. See how here, though, concave up, plus, concave up. It didn't switch signs. It didn't switch concavity. That's not an inflection point. It's cusp. So, not an inflection point. Over here, it went from concave up to concave down. That normally would be an inflection point, but one of the things is you have to be in the domain. See how there's like no value there? If I try to plug my C into my original equation, I would get nothing. It wouldn't work. You get no solution. So that's actually not that's not an inflection point because your A has to be in the domain. And then right here, you went from concave down to concave up. You switch. That's an inflection point. If you're doing a sign chart, this will be a positive. Sorry, this will be a negative because it's opening down, and that'll be a positive. So that's how you get. That's how you get an inflection point. Second derivative has to set equal to 0 or undefined, and you have to get a sign change. And then also, if you plug it back in, it has to work, right? In this case, I'll get a sign change, but if I plugged it back into my function, I wouldn't get a value. There will be no solution. So it has to be a sign change, and it has to work when you plug it back in. Okay, let's talk about formally how we do this. Right, just like last time. Right, first step we're gonna do is find all zeros where f double prime of 0 is equal to 0 and define. Right, these are my possible inflection points. Very important, possible. Right, to make an inflection point, it has to be a sign change and stuff. Part 2, plot. Right, we're gonna do a sign chart. So once you get your possible points, you do a little sign chart. We're gonna do little intervals and stuff. Pick a test point each side. And again, I can't stress this enough. We're doing the second derivative, right? This concavity is all about the second derivative. So we're going to plug our test points into the second derivative. Right? And like we talked before, if you get a positive, concave up. If you get a negative, concave down. And then again, if concavity changes between from the interval A to B, AC to CB, then we call that an inflection point. Right, so if you have, let's say we have a little thing here. I do A, B, C, and let's say plus, minus, minus, plus. My inflection point would be here because I switched from positive to negative. That's an inflection point. That would be A, then whatever it is after I plug it in. B would not be an inflection point. It went from negative to negative. Didn't switch signs, so not an inflection point. C would be. You switch signs. Yeah, I would check when I plug C back into the function that it works, but if it does, still an inflection point. I don't care if I got it from undefined. Still an inflection point. So that'll be an inflection point too. Just gotta make sure when I plug it in, it works. But that's how you find concavity, right? Second derivative equals 0 or undefined. Get your critical points. In this case, we're gonna call them possible inflection points. Do a sign chart. If it actually happens to switch signs, then it's an inflection point. As long as you plug it in, it still works. And anywhere it's positive is concave up, negative is concave down. So, next up, let's do an example. So here we go. Find the points of inflection of f of x equals 3x to the 5th minus 5x to the 4th plus 1. So, first, then determine concavity. Right, first, the second derivative. Right, so f prime of x, the first derivative, 15x to the 4th minus 20x cubed, 1 goes away. If I want to do increasing, decreasing, I'll find the critical points here. But I'm looking for concavity. So let's keep going. Let's take the next derivative, right? Take it again. 60x to the 3rd minus 60x squared. Right, so that's my second derivative. Next, let's find the possible inflection points. Set equal to 0 and factor. And notice they all have an x squared and a 60. We'll miss the 60. That'd be embarrassing. So 60x squared, x minus 1. Split it 60 x squared equals 0, x minus 1 equals 0. People freak out with this. I don't understand why. Guys, if there's nothing, if it's a monomial, just an x with nothing else like plus or minus, it's going to be 0. Divide by 60, x squared equals 0. Square root it, x equals 0. Every single time. Over here, see, there's a plus. Add it to both sides, x equals 1. So again, these are my possible inflection points. I'm not sure if they're inflection points. I gotta see if there's a sign change. And I gotta see if I plug it back in if it works. So, still a sign chart. We got 0, we got 1. Just like before I start, let's do a little interval here. This would be negative infinity to 0. This would be 0 to 1. This will be 1 to infinity. Right, so these are my concavities. Concave up, concave down. Just don't know which one yet. So, next step, let's pick test points. Negative 1. This kind of sucks. 1/2. So 1/2. And then let's say 2. Now again, it doesn't matter if you plug it into here or here. Now remember, a lot of the times you're not going to have a calculator to do this. So you got to learn how to start doing it without a calculator. And the key thing is, all you care about is the sign. That's why I like to use this one right here. Right? If I use 60 x squared x minus 1, hope you guys notice that right here, that's a squared, which means it's never going to be negative. It's always positive. So this right here is always positive. I just got to worry about this side, right? I really just got to plug into this thing, because if that's negative, then a positive times a negative is a negative, right? Good old grammar school rules. And if that's a positive, then a positive times a positive is a positive, right? So that's all you have to do is worry about the sign change here. So let's look at this one, right? Again, I know outside is going to be positive from that, because it's squared, automatically positive. Let's plug a negative 1 in. I'm going to get negative 1 minus 1, which is negative 2. A positive times a negative is a negative. So that's concave down. Let's look at 1/2, right? I know the outside's a positive. I'm going to plug 1/2 in. 1/2 minus 1. Well, 1/2 minus 1 is a negative still, because it's a negative 1/2. That positive times a negative is a negative. So that's also concave down. So concave down, concave down. So no inflection point, because I didn't get a sign change. And then let's plug in 2. Again, I know the outside is a positive. Plug it in there. 2 minus 1 is 1, which is a positive. So positive times positive, positive. Concave up. And I have a sign change. Woo! Got an inflection point now. Right, because we switched signs, so we have an inflection point. So my inflection point happens at x equals 1. Now the problem here is a lot of times they want the actual point. They're going to say, hey, what's the actual point? So your x is 1. Remember, how do you find the y? It's always the same thing. If you want to find the y value, you go back to the original function. Right? It's a point on the function, so you have to plug it in there. So if I want the y value for an inflection point, we're talking about the function itself, so you plug it in. So 3 to the 1 to the 5th, minus 5, 1 to the 4th, plus 1. Do a little, 1 to any powers is 1, so 3. Same idea, 5 plus 1. Negative 2 plus 1 is negative 1. So that's my inflection point, 1, negative 1, if I want the actual point. Sometimes they just want the x value, sometimes they're jerks and they want the actual point. So you gotta live with it. Right, so that's my point. If I want concavity, I have it right here. I can rewrite it to make it a little nicer for you guys. Concave up, I guess not much nicer, is 1 to infinity. Concave down will be these two, negative infinity to 0. Union 0 to 1, right? So that's my concavity. Let's run it back. Let's do another one. So look at this one. F of x equals x to the 5/3. Same idea of finding inflection points, blah, 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 blah. Right? So let's take our first derivative. Bring the 5/3 down, subtract 1 off. 5/3. Right? Subtracting 1, common denominator, 3 over 3. And I get 2/3. Take the second derivative, just do it again, right? You'll bring this down. So remember, when you multiply fractions, so 5 times 2 is 10, 3 times 3 is 9. Subtract 1 off, and I get negative 1/3. So that's my second derivative. Instead equal to 0, so 0 equals 10 over 9, x to the negative 1/3. Now, it's a little important, but I know the answer to be 0, right? It's a monomial. We talked about this right now. No plus or minus, answer to be 0. But let's keep in mind, I do want you to notice that, let me flip that it's not a 0 from it's from it equaling 0, it's actually from undefined. Because if you flip that, because it's a negative, you get this 10 over 9 x to 1/3. So there actually isn't no where the derivative equals 0. It's actually just undefined because it's on the bottom. So if we were solving this, 9x to 1/3 equals 0. Again, still going to be 0 because you divide by 9 and take third power both sides. But that comes from the undefined. Just how we know. So, but still a possible inflection point. That could still be an inflection point. Not the biggest deal in the world. Just that's one clarification. So you have 0, right? So my intervals are going to be, it's only one possible inflection point, -infinity to 0, and then 0 to infinity. As we always do, pick a test point each side. So like -1, 1. Now you plug it in. So again, I don't care if you plug into here, there, or there. It doesn't really matter. I'm plugging here just to be safe, so you can see what happens. But again, it didn't matter. You plugged in there also. Now here's the thing. This is a third root. Third root does do, right? Odd roots do negatives fine. Even roots would make a problem. If I was an even root, I would have no solution. I wouldn't have an increase and decrease right here. But this is an odd root, so it works. I just get a negative 10 over 9. So that's a negative. Concave down. On this side, plug the 1 in. 10 over 9 to the 1 to 1/3. Well, that's just going to be 10 over 9. Positive. Concave up. And then, since I switched signs, we get that's an inflection point. Yay. Right? Switch signs. Inflection point. Now we do want to test to make sure actually it's an inflection point, because I know I have x equals 0. How do we test? Well, it's switch signs, that's done. We got to make sure when I plug it back in, it actually works. So, 0, plug it in, right? Find the y value of the inflection point. This is why they ask you for inflection point, by the way. It's a little test, right? Plug it in. Well, 0 to the 5/3 is 0. So it actually works, right? There's no problem with 0. So I do have an inflection point. It's at 0, 0. So even though that was an undefined value, didn't matter. Still the inflection point. Because on the original graph, it won't be undefined. So that's how you find concavity and inflection points, right? Very similar to what we did last time. This time, find the second derivative, set equal to 0, find your possible inflection points, do a sign chart, right? Pick test points, plug it in, all the same stuff. If you have a sign change, that makes it an inflection point. If there's no sign change, it's not an inflection point. Okay. Let's talk about how you tell the concavity from other graphs. So first, let's say you have the first derivative. Right? How would you tell where the inflection points are in concavity? Well, it's just like always. If this is the first derivative, we're trying to get to the second derivative. Right? So what are the critical points? Here and here, right? Where it's a max or min. Right? It's like we always do. If you're trying to get to the next derivative, it doesn't matter if it's the first to the second, second to the third, or the original to the first. The critical points are your max and mins. So again, you want to treat this like a sign chart. -2 and 0 max values. And then, right, notice how it's increasing. So that's going to be positive because we're trying to get to the second derivative. It's just like doing a chart. It might just be easier to make a graph, actually. Here's -2 out of 0. If it's 0 there. Increasing, so positive. Decreasing, so negative. Increasing, so positive. Right, so before that, positive. In between, negative. After that, positive. And just like always, concave up, inflection point, it switch signs, yay. Concave down, switch signs, yay. Concave up, inflection point, 2 inflection points. Right, that's the kind of idea. Anytime you want to go from one derivative to the next, it's always just easier, honestly, just to make the graph. And then look at it that way. So you're like, okay, here, where's my critical points? Right there. So my second derivative, it's going to be right there. Decreasing, so negative. Increasing, so positive. So if I was trying to do a sign chart, terrible one, I only have one critical point at 1, right? It's negative, so it's decreasing, so negative, and then it's increasing, so positive. So it'll be concave up from -infinity to 0, and concave down, sorry, and then concave up from 1 to infinity. And then it switched signs, so there's an inflection point. Yep, yay. So that's the idea. Like anytime, this is true for anything, right? If you're trying to go from one to the next derivative, you're looking for the max and mins, like your critical points, and you could just draw it. And then from there you could tell, okay, positive, negative, positive. What's far more interesting is when you go backwards. Right? Look at this one. Right here they're telling you, hey, here's the second derivative. So based on the second derivative, what's my inflection points and what's my concavity? Keep in mind, right? You're at the second derivative. That's what we've been doing all day, right? Second derivative equal to 0 undefined are your possible inflection points. When that second derivative is greater than 0, it's concave up. When it's less than 0, it's concave down. So I always say treat this like a sign chart already. You have your critical points, the zeros, your possible inflection points, 1 and 2. Right? You have the graph itself. Oh, this is positive. This is negative. Positive. Right? It's actually easy if you understand what's going on. Wait, second derivative? I'm at the second derivative, so the zeros are the inflection points, possible inflection points. Right? Positive isn't up, negative is down. Right? And then you notice it switched signs, so this is an inflection point. It switched signs, so it is an inflection point. Yay for both. Right? This is concave up, which would be negative infinity to 1. Concave down from 1 to 2. Right? So 1 to 2 is concave down. And then concave up again. Right? 2 to infinity and negative infinity is concave up. Negative infinity to 1. Union 2 to infinity. So that's the idea. Right? So you just want to treat it like it's a sign chart. Just look at, again, it really does matter which one you're talking about. If you're talking about the derivative, you're like looking at it. If I'm talking about the original graph, we did way up here. Right? Well, if you look at the original graph, concave up is just the way it's opening. Opens down, opens up, concave up. If you're looking at the derivative, you're like, wait, if I take the derivative again, I get concavity. So you're looking for the max and min points. If I give you the second derivative, you're like, wait, I'm here. So where are my critical points? Well, where it's equal to 0 at. Okay, now let's put this all together. So let's look at this one. This is one that looks hard if you understand what each thing does, and it's actually not bad at all. Right? So here's my f of x. It wants me to fill out each of this little table here with f prime of x. Is it positive, negative, or 0? F of x, f prime of x, and f double prime. The key here is, what does this thing mean? Right? When you're talking about f of x, you just look at the graph. It's just the position. Right? Look at A here. A is positive. It's above the graph. Right? If you're above the graph, you're positive. You're below, you're negative. If you're on the line, you're 0. Right? It's this position. The original function is just a position. So A, above the graph, positive. Let's look at B. B is below the graph, so negative. C, it's a little bit above the graph, so positive, above the x-axis, sorry. D is up here, right? Again, still above the x-axis, so it's positive. E is right on the line, so 0. Right? If you know what that means, it's not that bad. You just go, oh, is it above or below the line? Same idea for f prime. Right? Think about, what does f prime mean in what we've been doing? It tells us the increasing, decreasing. That's what it tells us. So all you want to do is look at, is it increasing or decreasing at that point? Look at A. Is that increasing or decreasing? Well, the graph's going down, so it's decreasing, negative. At B, that's the tricky part. Notice that's a max or min. Those are the critical points. So it's not increasing or decreasing. It's like at the very bottom. So it's 0. Right? Remember when we take the derivative, you look for the zeros at the max and min. So it's not increasing or decreasing. C, it's going up. It's increasing, so positive. D, notice again, at a max or min, so 0. E, going down, so negative, decreasing. And then the same thing for this final one here. Second derivative. Remember what that's what we've been talking about all day today. That's concavity. Right? I should have done this here. Increasing is plus, decreasing negative. Right? Concave up. If your graph's opening up, it's plus. If it's opening down, it's a negative. So let's look at, I'm gonna write on this graph a lot more now, right? From here to here, your graph's opening up. So A and B are both positive. The graph's opening up. C is an inflection point. That's where it switches. So that's a 0. Then look at this part. Your graph's opening down from here to here. So those are both going to be negative. Right? Because that's what it means. Concavity is it opening up or is it opening down? Right? First derivative is increasing, decreasing. Is it decreasing or increasing? And f of x is this, where is it at? Is it above or below the line? Right? If you understand that concept, this stuff's a breeze. And that's it for today's lesson.